Hi, today I'd like to do a quick introduction for Hertzsprung Russell diagrams at advanced higher physics level. This is a Hertzsprung Russell diagram, or an HR diagram. And these are used in astronomy an awful lot. They're used to categorize stars and see how stars can be similar to each other and how they can be different from each other. We're going to be looking at why the stars are in the different places in this diagram and what that basically means. This lesson. Next lesson, we'll maybe look at how the stars actually can actually start in one place and can actually end up somewhere else as their lifetime goes on, as they get towards the end of their lifetime. For the moment, what we're interested in is what this diagram is actually showing. Along this axis here, we have temperature, and along this axis here, we have luminosity. Now, temperature is really important from the point of view of stars. It tells you an awful lot about what the star is doing. You might notice here as well as temperature, we've actually got colours and we've got these letters. Well, these letters are actually designed to correspond to colours, and they're used by astronomers when they're looking at a star in the sky. Most stars, when you just look at them with an unaided eye, look pretty much the same. They look white and sort of sparkly. Or possibly not sparkly, but they certainly look white. But when you look at them through a telescope or through a pair of binoculars, you can see that they actually have colours. The colours of the stars are dependent on their temperature. This is something we've looked at before, so I'm not going to go into it in great detail. But basically, the peak wavelength of the stars, so that's the wavelength, the colour of light that they're giving out the most, depends on temperature. Again, we looked at this in higher and we looked at this in the last lesson, but generally speaking, the peak wavelength of stars that have got lower temperatures are actually are closer to the red end of the spectrum, and the peak wavelengths of the stars with higher temperatures are closer to the blue end of the spectrum. You don't need to worry too much at advanced higher physics about these letters. Something else you'll probably notice here is that the temperature is actually decreasing along this scale. That's deliberate, and there are reasons for that we don't really need to go into at the moment. But basically, it makes it work much better. If we're looking up on the y-axis is the luminosity. Now, you remember from a couple of lessons ago, the luminosity is basically the power of the star, the actual power of the star, not the brightness that we see at Earth. The reason for that is that a very bright star that's far away will look rather dim, but it doesn't mean to say that it's actually giving out any less power. It's just because we are further away. So this is the actual luminosity. Now you can measure the actual luminosity in actual watts, or you can measure it in solar units. And a lot of the time, just to make it a little bit easier, we tend to use solar units. So what's a solar unit? Well, a solar unit is basically, it's measured by the sun. So our sun has a solar unit of 1. Right? That's just by definition. So there's our sun there, and it's a solar unit of 1. Those that have a luminosity of giving out 10 times as much power as the sun would have a luminosity in solar units of 10. And then you go up to 100 times, 1,000 times, 10,000 times, and so on and so forth, the power of the sun. Going down the way, it goes a tenth, 100th, 1,000th, and so on in that direction. So this is called a logarithmic scale. If we didn't have a logarithmic scale on both axes, because this has got a logarithmic scale too, if we didn't have a logarithmic scale on both axes here, then what would happen would be we'd have a diagram that would be so large, it would take up most of the solar system to actually make sense of it. There are certain patterns when you're looking at these diagrams. The first, most important bit here is called the main sequence. The main sequence of stars is where most stars are found during their lifetimes. At one end, we have very hot, very bright stars. These are stars that are giving out a lot of power and a very high temperature. At the other end, we have stars that are low temperature and are giving out much less power. Our sun is sort of close to the middle of this. By the way, I should say the temperature that we're talking about is the surface temperature. The temperature inside most stars where nuclear fusion is taking place is going to be millions of degrees. But the surface temperature of these stars is actually a lot less. Right, so most stars are on this main sequence. Now the ones up here are the ones that probably live fast, die young. They're the ones that have very high temperatures. They're giving out a lot of energy. They're really burning themselves up. The ones down this end of the cycle, this end of the sequence, are living a lot more slowly. These stars you're talking about lifetimes in terms of hundreds of billions, trillions, or even more years. And these stars, some of these have been around for an awful long time. The ones up here, they don't live very long in universal scale. They're maybe talking about 10 million years, which is actually barely a blip in terms of the lifetime of the universe. There's another couple of groups of stars. Up here we've got giants and supergiants. Now these are basically stars, normally at the end of the lifetime. It's one of the main sequence stars that's come to the end of its life. We'll have a look at this in the next lesson, so I'm not going to go into it in great detail. But that basically, for various reasons, have actually got a very low temperature, but are actually giving out a huge amount of energy. Now the only way you can do that is if you're absolutely huge. So that although the surface temperature is actually relatively low, only about 3000 Kelvin or so, these stars are giving out energy over a massive, massive area. And the difference in terms of size is enormous. We'll have a look at this in a wee second, but it's over a huge, huge size. And so therefore, they actually do appear to be quite bright in the sky. The stars down here are called white dwarfs. These are another way that stars can actually end their lives. We'll look again at this in the next section. But the white dwarfs are down here, and these are stars that actually still have quite high temperatures, but they're not giving out very much power in total. And the reason for that is that they're actually quite small. If you've got a high temperature, then you have to give out a very high power per unit surface area. So per square meter, they're giving out a lot of power. They're really, really hot. But their surface area is an absolutely tiny fraction of the supergiants up here. So the total amount of energy they're giving out is actually not that big. And this is the last bit that I wanted to mention in this diagram. Along here, you have the solar, you have these lines here. These lines here basically cut across this diagram at diagonals. And what we find is that any star that's on this line will have 0.1 solar radius. So that basically means it's going to be a tenth of the radius of the sun. Our sun obviously will sit on 1 solar radius. The stars up here are on 10 solar radii. And then by the time you get up to the supergiants up here, we're talking about 1,000 times the radius of the sun. So they're absolutely massive. In comparison, going the other direction, white dwarfs might be sitting around about 100th, 10 to the minus 2, 100th of the diameter of the sun. So that's the information that we need to get from one of these charts. This chart here plots thousands of different stars. It's basically the same as the previous one. We've got either colour or spectral class and temperature. Temperature is the one that we're going to meet at advanced higher level, against the visual luminosity, which is just another word for the luminosity compared to the sun. Okay, so this is actually what we're looking at, and we can see the patterns very, very clearly here. We can see the majority of the stars in the main sequence. We can see the fact that there's a fairly large clump that would be categorized as giants up here, and some stars are actually, I would say, making their way into this giant cluster here. And we've got a few stars sprinkled up the top here in what would be called the kind of the supergiants. There's a few open areas here. We're not going to go into why these areas exist, but the fact is that you don't really find many stars in there. But what you do find is this cluster of white dwarfs. White dwarfs basically are all found along this line at the bottom, where we're talking about very low luminosities and relatively high temperatures. So kind of blue coloured stars, but they're actually fairly faint. They're not giving it a huge amount of power. Just one wee thing. On this side, we've got something called absolute magnitude. This is another way that astronomers talk about the luminosity. We're not going to go into that. It's just another measure. And this, just to kind of finish up, is an SQA question. Okay, this is the type of question that you might get, and again, you can see that it's simplified a little bit, so you're not kind of overcrowded with information, but it gives you a wee idea about the size of stars, about the luminosity in solar units, and about the temperature. Actual question here is it gives you some information, and it basically asks you two things. First of all, it says, on the HR diagram, circle the star at the position of Procyon B. I don't know if the pronunciation is right. Apologies to those of you who know better. They basically tell you a little bit about it. They tell you it has a luminosity of 4.9 times 10 to the negative 4 solar units, and a radius of 1.2 times 10 to the negative 2 solar radii. This isn't in meters. This is basically as a fraction of the sun's size. So we're around about 10 in order of magnitude. It's around about 10 to the minus 2 radii. So it's going to be something along the lines of here. Probably a little bit bigger than it. So maybe this one. Maybe this one here. That's a little bit smaller, so it's probably not likely to be that. Okay, so it's going to be one of these two. We need to have a look at its luminosity. So its luminosity is 4.9 times 10 to the negative 4 solar units. So that's basically kind of 10 to the negative 4. So it's going to be a little bit bigger than that. So if we look along, it's going to be this one here. This is the one on the graph. Sometimes a wee bit harder to do because we do have a logarithmic scale here, but it gives you, and also I suppose up here, but it's basically just identifying this. So that's all they're asking you to do. And the second one is saying what type of star is Procyon B. Well, because it is below the main sequence here, and it's in this little group of stars down here, it's really likely to be a white dwarf. I can't unfortunately show you the other diagram at the same time, but it's likely to be a white dwarf. And that's really all they're asking you to do. So don't worry too much about the amount of information here. You just need to have an understanding of what's going on, and you should be absolutely fine. If you want to do more reading though, there's plenty of stuff out there on the web. It's certainly a topic and a subject that's got lots of really great understandable videos that will help you.